Good evening, class. Here's exam review. Section 3.9 to 3.11, 4.1 to 4.5. Here's part 3, section 3.11, hyperbolic functions, 4.1 maximum and minimum values. So, hyperbolic functions, what do we know about it? Here's a definition from pre-calculus, college algebra. Cosh x, or hyperbolic cosine, equals e to the power of x plus e to the power minus x over 2. Sinh x, or hyperbolic sine, equals e to the power of x minus e to the power minus x divided by 2. This is by definition. Hyperbolic functions are called hyperbolic because they are defined in relation to a hyperbola, just as trigonometric functions are defined in relation to a circle. Trigonometric functions come from a point on this circle, unit circle, x squared plus y squared equals 1. Therefore, cosine squared plus sine squared equals 1. A point with coordinates x, y, p having coordinates x, y, is the same as having coordinates cosine t, sine t. So x represents cosine, y represents sine. Sine t equals y, cosine t equals x. Now, unit hyperbola, x squared minus y squared equals 1. In this case, cosh squared minus sinh squared equals 1. And a point with coordinates x comma y is the same as cosh t sinh t. In other words, sinh t represents y and cosh represents x, similar to what we mentioned in the case of trigonometric functions. So having said that, there are definitions with trigonometric functions. For example, tangent is sine over cosine. Same thing with the hyperbolic functions, similar. Hyperbolic tangent is sinh over cosh. Hyperbolic cotangent is cosh over sinh. Cosecant, remember, is 1 over sine. So hyperbolic cosecant is 1 over sinh. And hyperbolic secant is 1 over cosh. Very similar to what we have seen. Now, there are some identities that are similar or close. For example, we know cosine squared plus sine squared is 1. In this case, cosh squared minus sinh squared equals 1. A hyperbolic cotangent squared minus 1 is hyperbolic cosecant squared. 1 minus hyperbolic tan squared equals hyperbolic secant squared. A sinh 2x is 2 sinh x cosh x. As you recall, sine 2a is 2 sine a cosine a. Cosh 2x is cosh squared plus sinh squared. Cosine 2x was cosine squared minus sine squared. So cosh squared is cosh 2x plus 1 over 2, and sinh squared is cosh 2x minus 1 over 2. Similar, not exact. Sinh minus x is minus sinh x. Cosh minus x is cosh x. If you remember, trigonometric functions, they are all odd, with the exception of cosine, and therefore secant. So same thing here. Sinh is an odd function, cosh is an even function. Sinh x plus y, you remember sine of alpha plus beta. Okay, sine alpha cosine beta plus cosine alpha sine beta. So sinh of x plus y is sinh x cosh y plus cosh x sinh y, and cosh x plus y is cosh x cosh y plus sinh x sinh y. Now, for example, if you want to prove this one, just look at this one. Cosh of minus x. Over here, replace the x with minus x. So you get e to the power minus x, e to the power minus minus x. This one is the same as e to the power of x. And I hope you see that this becomes identical to this one. That's why cosh minus x equals cosh x, and that's an even function. Hyperbolic derivatives, remember the derivative of sine, for example, is cosine. So the derivative of sinh is cosh, the derivative of cosh is sinh. The derivative of cosine was negative sine. So there are some similarities, some differences. And the proof is very simple. Just differentiate here and you'll see the answer. The derivative of hyperbolic tangent is hyperbolic secant squared. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. And the rest of them follow in the same manner. Sinh inverse becomes natural log of x plus square root of x squared plus 1. Cosh inverse of x is natural log of x plus square root of x squared minus 1. And hyperbolic tangent inverse is half of ln of 1 plus x over 1 minus x. In this case, x is all real numbers. This one x larger than or equal to 1, and this one between negative 1 and 2. And again, finding them is very simple if you look at, for example, Cauchy inverse. Over here, you can derive Cauchy inverse and take it from there. So you can call this y equals Cauchy x, which is e to the power of x minus plus e to the power minus x over 2, and then interchange x and y, you come up with the answer. You recall the derivative of sine inverse is 1 over square root of 1 minus x squared. The derivative of cosine inverse is the same thing with the negative at top. And the rest of them, we have the same thing for sinh. The derivative of sinh inverse is 1 over square root of x squared plus 1. The derivative of Cauchy inverse is 1 over square root of x squared minus 1, and so forth. And again, to differentiate, you can differentiate this. You know how to differentiate a natural log, and that will be the proof. Now, we're going to look at a couple of proofs here. So, for example, we want to prove that Cauchy squared minus sinh squared equals 1. As you recall, in trigonometry, in order to prove identities, we would start with the more complicated side. In this case, obviously, the left-hand side, Cauchy squared minus sinh squared. So we're going to replace the Cauchy with e to the power of x plus e to the power minus x over 2, and sinh with e to the power of x minus e to the power minus x over 2, and each one will be squared and negative in between. So what happens here? Both of them, the denominator is 4. This one, e to the power of 2x plus 2 e to the power of x e to the power minus x plus e to the power minus x. And this one is the same thing with the negative in between. I am following a plus b quantity squared. And remember, this one is minus 2ab, okay? Now we're going to put them together. And first and foremost, I want you to notice e to the power of x times e to the power of minus x is e to the power of 0, which is 1, and this is 2. And this is the same thing, 1 times negative 2 minus 2. So we are going to write this one as it is. This one, we're going to change the sign because of the negative. Minus e to the power of x, minus e to the power of 2x, minus and minus, plus 2, minus e to the power minus 2x. So the numerator is 2 plus 2, 4 over 4 equals 1. So that's a proof. Very straightforward, everybody. So in order to prove identities such as Cauchy squared minus sinh squared, we go to the definition. What about this one? I hope you remember when we proved Pythagorean identities after the first one, then we used the original one and got through the other two. For example, sine squared plus cosine squared was 1, and 1 plus tan squared was secant squared. Now, what do we do here? We do exactly the same thing as far as the methodology is concerned. We start with what we just proved. Cauchy squared minus sinh squared equals 1. We're going to divide both sides. Because we want 1, we're going to divide both sides by this one, which is Cauchy squared. When we do that, obviously this becomes 1. Sinh over Cauchy is hyperbolic tangent, so minus hyperbolic tangent squared. 1 over Cauchy is hyperbolic secant, so squared, because this is squared. And believe it or not, that's the proof. So proving is very similar. The process of proving things here is very similar to proving identities as we did it in trigonometry. Okay. All right. We are saying that the derivative of sinh is what? We are saying it's Cauchy. Let's prove that. Well, d dx of sinh x, we are going to replace the sinh with its definition, e to the power of x minus e to the power minus x over 2. So if I want to differentiate this, of course, remember 1/2 in essence is the coefficient that remains. So this becomes itself minus e to the power minus x times -1, that becomes plus. And I hope you see that's identical to Cauchy. So it's a very simple proof. So what is the derivative of sinh of 10x squared? And I hope you recognize this one as a function of x, and therefore we are going to use the chain rule. So the derivative of sinh g of x is cos g of x times g prime. This comes from the chain rule. Or sinh u is cos u du dx. So the derivative of sinh is cos, so cos of 10x squared. And then, so again, just the way I did it with trigonometric function sinh and pause, the answer is cos. You have to write the argument, which is 10x squared. And now 10x squared, the derivative is 20x. This is the chain. And we rewrite it by putting the 20x in front. 20x cos of 10x squared. So that's pretty straightforward, everybody. What about the derivative of cos square root of x? We do the same thing. The derivative of cos is sinh. But sinh, again, cos, and I'm going to pause, the answer is sinh. But you can't write it without the argument. You have to use the same argument, square root of x. And then times the derivative of the square root of x. By now, you may know it's 1/2 square root of x. If you have doubts, just write down square root of x is x to the power of 1/2. You want to differentiate it 1/2. X to the power of 1/2 minus 1 is -1/2. And it's this one, and you just rewrite it. Sinh square root of x over 2 square root of x. Let me erase my work. So it's pretty straightforward, everybody. What about hyperbolic tangent of 1 plus e to the power of x? And remember, hyperbolic tangent, the derivative is hyperbolic secant squared. So just this one, hyperbolic secant squared. But hyperbolic secant squared of what? You have to use the same argument, 1 plus e to the power of 2x. And now we are going to use the chain rule, and we're going to differentiate 1 plus e to the power of 2x. 1, 0, e to the power of 2x is itself times 2. This is done. We're going to rewrite it by putting this in front. So 2 e to the power of 2x, hyperbolic secant squared of 1 plus e to the power of 2x. Very straightforward, everybody. What I call sinh inverse of x squared. We want to differentiate that. And the derivative of sinh inverse is 1/x squared plus 1. And if it happened to be a function, then times, let's say it's g of x, then times g prime of x. So it's important to understand that The derivative of sinh inverse of u would be du dx, square root of u squared plus 1, if we call it g of x, would be g prime over the square root of g of x quantity squared plus 1. So with that being the case, we are going to rewrite it in this fashion, 1 over something here plus 1, okay? And that has to be squared up. So what goes in here? Whatever this function is. Which is x squared. What goes in here? G prime, or du dx, 2x. And we put them all together. 2x in the numerator, square root of x to the power of 4 plus 1 in the denominator. And that's the final answer, everybody. Sinh inverse of tan x. We're going to do exactly as we did here, and this is g prime over the square root of g of x quantity squared plus 1. So we write it in this fashion. Then over here, we have a parenthesis, something to the second power. And what is to the second power? Whatever that one is, happened to be tan x. And then its derivative is secant squared x goes in here. Again, I'm showing you step by step, everybody. And finally, we just rewrite it. This is secant squared over tan squared plus 1. Tan squared plus 1 under the radical is secant squared, everybody. As you know, the square root of secant squared is really absolute value of secant x. So this is really absolute value of secant x. I hope, again, reminding you that this one is absolute value of x. I hope you remember that. So therefore, when we divide that, the answer is again absolute value of secant x, okay? So secant squared divided by absolute value of secant x results in absolute value of secant x. And that's important to understand. Let me erase my book. So we notice, in this case, part C, y equals e to the power of x times cos x. So I'm going to put a raised dot in between and say, okay, this is f times g using the product rule. F prime g plus g prime f. So f prime e to the power of x is itself times g cos x. And our g prime, the derivative of cos is sinh x, times f e to the power of x. And I'm going to take the common factor of e to the power of x out. And I get this one. Now, what's interesting here is that cos x and sinh x, if we add them up, what do we get? So take a look at this one here. If you add these two, what do you get? E to the power of x plus e to the power of minus x plus e to the power of x minus e to the power of minus x. These two cancel each other. So you get 2 of that over 2. I hope you see that their sum is e to the power of x. I hope you see that this is e to the power of x, everybody. Just add these two and you'll see that. So therefore, e to the power of 2x is the final answer, everybody. So that's pretty straightforward. I hope everybody's following that. All right. Application of differentiation, chapter 4, maximum and minimum values, the mean value theorem, how derivatives affect the shape of a graph, indeterminate forms, and L'Hopital's rule, summary of curve sketching. And then this one belongs to the next exam. So having said that, let's start with 4.1. Maximum and minimum values. Definition, critical point short CP. A critical number or point of a function f is a number c such that f prime is 0 or f prime does not exist. Find the critical numbers for y equals x to the power minus 2 ln x. So to do that, first and foremost, we have to differentiate. So what is the process? Number one, find f prime. Number two, set it equal to 0. Number three, see where f prime does not exist. That's how you find all the critical points. So to do so, we are going to put a raised dot in between. Okay. FG, the result is f prime g plus g prime f. So this one is negative 2x to the power of negative 3 times ln x plus ln x is 1 over x when you differentiate times x to the power minus 2. So this one doesn't change, but this one is x to the power of negative 3. I hope you see that. You can bring it up x to the power minus 3. And so both of them, I can take x to the power minus 3 out. This leaves me negative 2 ln x plus 1. And I'm going to rewrite it such that x to the power minus 3 goes down, becomes x cubed. So this is y prime. F prime is 0. A fraction is 0 if the top is 0. So fraction a over b is 0 when a is 0, undefined when b is 0. So for now, the top is 0. And so that means ln x is positive 1/2. You can take this to the other side, to the right, becomes negative 1 divided by negative 2 is positive 1/2. And now ln x is 1/2. That means, let's go with the arrow, x is e to the power of 1/2 precisely. Also, f prime doesn't exist. The denominator equal to 0. X equals 0, but it can't be because it's not part of the domain. Why it's not part of the domain? Let's go to the original function. The fact that this is a product of x to the power minus 2 and ln x says that x must be larger than 0. Although this is ln x over x squared. X can't be 0 anyways, but this has a bigger limitation. So this has the domain of 0 to infinity. That covers the fact that this is in the denominator. Okay, so that's pretty straightforward, everybody. Formal definition, maximum or minimum points on a curve. Local, also known as relative extreme values. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at the point C in an open interval of a to b in the domain if f of c is less than or equal to f of x for all x values in the open interval. A local maximum is the maximum value within some open interval. Local maximum occurs at the point C in an open interval a to b in the domain if f of c is larger than or equal to f of x for all x values in the open interval. In other words, Peaks and valleys. Local max, local mean, local. That's all. That's the meaning of it. It happens in some open interval, not the entire interval. Whereas absolute or global happens in the entire interval. Absolute or global extreme values are either maximum or minimum points on a curve. Absolute minimum occurs at the point C if f of c is less than or equal to f of x for all, that's the key, all x values in the domain, whereas absolute minimum occurs at the point C if f of c is larger than or equal to f of x for all x values in the domain. So as we look at these two cases, please understand this is a local mean, local max, local mean, local max, local mean, local max. This local minimum is also absolute. So peaks and valleys, they are always local. Then you further investigate. This one is a local minimum because it's a valley, but it is also an absolute because no other point has a smaller y coordinate. This one is a local maximum. Also, it's an absolute because no other point has a larger y coordinate. That's how you figure it out. Local or relative extreme values. According to Fermat's theorem, if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists, then f prime must be 0. As we look at these two, I hope you see that you have a horizontal tangent line which has a slope 0, local max, local mean, and the derivative does exist. However, this one is a sharp corner. F prime does not exist. So this is a local maximum. And according to this graph, it's also an absolute maximum, okay? By the way, endpoints can only be absolute. They can never be local extreme. Local extremes. In the interior of the function occur where f prime is 0 or f prime is undefined. Maxima and minima of a function always occur at critical points. But critical points are not always maximum or minimum values. You have to further investigate them. They may or may not be. And now we have the extreme value or closed interval theorem as a result. If f is continuous over a closed interval of a to b, then f has a maximum and minimum value over that interval. Take a look. Local max, local mean. It happened to be an absolute max here, absolute minimum here, if this is the entire domain. So maximum and minimum at interior points. This one, absolute max, absolute mean at the endpoints. Absolute max, absolute mean, one is interior, but one is at the endpoint. Maximum at interior, minimum at endpoint. So to find absolute max and minimum values by extreme value or closed interval theorem, number one, find the critical points, CPs, and evaluate the function at those points. Functional value at CPs, critical points. Number two, find the values of the function at the endpoints, f of A, f of B. Now, the largest value is the absolute max, the smallest value is the absolute mean. So, in the case of an extreme value theorem, or known as closed interval theorem, if f is continuous over a closed interval of A to B, then f has a maximum and minimum over the interval. So the key is closed interval, and I can't emphasize this enough. Find the absolute max and mean for this function, f of x equals 1/3 x cubed minus 9x, in the given interval of -6 to 0. So we have to discuss the type of function. This is the extreme value theorem. So this is a polynomial function. However, recall, all functions are continuous in their entire domain. I want to make sure everybody understands what that means. It means you have to be able to come up with a domain. When you mention the domain of a function, that's where the function is continuous. And every function is continuous in its domain. Its domain may be limited, but nevertheless, continuous in the domain. In the case of a polynomial, where f of x is a sub n x to the power of n all the way to a sub 0, where each a sub I is real, a sub n can't be 0, and n is a whole number, 0, 1, 2, 3 to infinity, the domain is all real numbers. So what do we have here? Polynomial of degree 3, which makes it continuous from negative to positive infinity, which makes it continuous in the given interval because this contains the given interval. So we are going to go with the extreme value or closed interval theorem. Number one, we want to find CP. That means we are going to differentiate. F prime of x, 1/3 times 3 is 1, x squared minus 9. Because we want to set this equal to 0, we're going to factor it into x plus 3x minus 3. And therefore, we get two answers. This gives us negative 3, this gives us positive 3. So that's the first part. The second part says where f prime does not exist. F prime does not exist doesn't give us any solution. This is phi which represents an empty set in set theory. That's a Greek letter. Now, why is that? F prime itself is a polynomial of degree 2. It exists everywhere. So we have two critical points. Can we use both of them? Is negative 3 in between? Yes. Is positive 3 in between? No. So you can only use the one in between. This is a notation, looks like an epsilon, and it reads an element of. In other words, negative 3 belongs here. Therefore, we are going to go back into the original function and evaluate the original function at these two endpoints as well as this critical point. So let me erase my work. So we're going to write the original function, everybody, f of x. And now we are going to plug in negative 6. When you cube it, negative 216 times 1/3, you're going to divide by 3, you get minus 72. This is plus 54. They add up to negative 18. Let's plug in negative 3. This is negative 3 cubed, negative 27 divided by 3 is negative 9, plus 27 is 18. And if you plug in 0, obviously you get 0. The third one, absolute max is the largest. So absolute max is 18 at this pair. Absolute minimum is negative 18 at this pair. The way you write it is the way they want you to write, okay? In other words, they may just want you to write absolute max. They want you to write at x equals minus 3 or the pair. So you follow accordingly. Find the absolute max and mean value for this function. F of x is x plus 3 to the power of 2 minus 5 in the interval of negative 4 to 5. So the question is, what's going on here? Well, we're going to rewrite this. So f of x is cube root of x plus 3 quantity squared minus 5. And ultimately, it's a cube root. And basic cube root looks like that with the domain being all real numbers. And what happens in this one, plus 3 shifts to the left by 3 and minus, and then gets squared up. So the negative side flips over and gets larger. The positive side just gets larger. Minus 5 bring it down by 5 units. So it's a cube root. The domain is all real numbers. And if it's continuous from negative to positive infinity, it is continuous in the given interval of minus 4 to. Therefore, we are going to go with the extreme value or closed interval theorem by differentiating. So to do so, I'm going to erase my work again. So this is 2/3 x plus 3 to the power of negative 1/3 because 2/3 minus 1. And then the derivative of the inside is 1. We don't have to write it. So negative 1/3 exponent goes down. So x plus 3 to the power of positive 1/3 or the cube root. Now we want to look at f prime is 0 or doesn't exist, reminding you that a fraction is 0 when the top is 0, undefined when the bottom is 0. So f prime equals 0, the numerator is 0, and it has no solutions. Why not? The numerator is a number. Doesn't matter, positive, negative, small, or large. There is no solution. F prime doesn't exist, the denominator is 0. And as you can clearly see, the denominator is 0 if x is minus 3. The question is minus 3 in between negative 4 and 5? Yes, we are going to use the end points as well as negative 3, the critical point, to evaluate the function f of x. So here's f of x, and we are going to put in those three numbers one by one. So if I put negative 4 here, negative 4 and 3, as you know, is negative 1. Cube root of negative 1 is negative 1. Square root is positive 1 minus 5 is negative. Negative 3, when I put it here, take a look. When I put it here, this goes to 0, just minus 5. What about 5? If I put 5 here, I hope you see 5 and 3 is 8. Cube root is 2. 2 squared is 4. Minus 5 is negative 1. They're all negative. The largest value, negative 1. The smallest value is negative 5. And we write absolute maximum is negative 1 at 5, comma, negative 1. Absolute minimum is negative 5 at negative 3, comma, negative 5. All right, we're going to repeat the question with this function, f of x equals x over x squared plus 2 in the closed interval of 0 to 4. Now, what type of a function is this? I hope you recognize this as a rational function. You said the denominator equal to 0, you excluded, that becomes the domain. In this case, the denominator, x squared plus 2 equals 0, that gives you no solution. It will never, ever be 0. Worst case scenario is 2. So believe it or not, although it's a rational function, the domain is all real numbers. So a function f is a rational function if f of x equals n of x over d of x. D of x can't be 0. That's how you find the domain, where n and d are polynomials. The numerator and the denominator must be polynomials. The domain of f consists of all real numbers except the zeros of the denominator of f of x, namely d of x. So set this one equal to 0, excluded. When we set it equal to 0, nothing happens. Therefore, although f is a rational function, it's continuous from negative to positive infinity. Therefore, it makes it continuous in the given interval of 0 to 4. So we are going to go with f prime of x, which means we are going to go with the quotient rule, and I'm going to write it here, f prime g minus g prime f over g squared. So x gives you 1 times x squared plus 2. X squared plus 2 gives you 2x times x, so minus 2x times x, and the bottom squared. We are going to simplify the numerator by combining terms in the following manner. X squared plus 2 minus 2x squared. These two add up. And f prime of x is negative x squared plus 2 over x squared plus 2 quantity squared. F prime is 0 if the top is 0. And that means 2 equals x squared, and x is plus minus square root of 2. F prime doesn't exist if the denominator is squared. As you recall, x squared plus 2, we said that equal to 0 had no solution. When you raise it to any power, the same thing. No solution. So that doesn't give us any numbers. So we have 2. Let's plug in. Square root of 2 is about 1.4. Is it in between? Yes. How about minus square root of 2? No. So you can only use positive square root of 2. So we are going to write the function f of x, and evaluate it at the endpoints and the critical point. So if I plug in 0, I hope you see clearly, we get 0 over 2. This is 0 over 0 squared plus 2. 0 over 2, which is 0. I'm going to put square root of 2. So this is square root of 2. This is 2 and 2, 4. So square root of 2 over 4. I'm going to put 4. This is 16. 16 and 2 is 18. And we get 4 over 18, which is 2 over 9. Now, if you don't recognize which one of them is largest, this is the largest, you just go with the decimal representation. But this is larger. This is about 0.2 bar. This is square root of is about 0.35. So absolute maximum is square root of 2 over 4, which is roughly 0.35 at this pair. And absolute minimum is 0 at 0, 0. We're going to find the absolute max and minimum for this case, f of x is x squared minus 1 quantity cubed, the closed interval of -1 to 2. The question is, it's important to know, can we use the extreme value theorem? Well, this is a polynomial of degree 6, continuous from negative to positive infinity, therefore continuous in the given interval. Therefore, we can use the closed interval theorem. So we start with the CP. That means we are going to differentiate this. To differentiate this 3, x squared minus 1 squared times the derivative of the inside 2x. And that becomes 6x times x squared minus 1 quantity squared. F prime equals 0, so set this equal to 0. Either x is 0 or x squared minus 1 is 0. So that means either this one is 0 or x squared equals 1. That's the meaning of it. So plus minus 1 and 0. F prime doesn't exist, doesn't give us any solutions because, as you can see, f prime itself is a polynomial of degree 2 squared 4 plus 1. I hope you recognize the degree is 5. So let's see what we can use. Can we use -1? It's one of the endpoints. Can we use +1? Yes, it's in between. Can we use 0? Yes, in between. So we're going to evaluate the function at all of the above. Okay. So the original function we write. I'm going to put -1. As you know, -1 squared is +1, -1 is 0, cubed is 0. If I put 0, this goes away. -1 cubed is -1. If I put 1, it works just like -1 because 1 squared is 1. -1, 0 cubed. If I put 2, I get 2 squared, which is 4, -1, which is 3, cubed, which is 27. Clearly, absolute max, absolute mean, the way we write it, absolute maximum is 27 at 227. Absolute minimum is -1 at 0, -1. That's how you write it.